time as an illusion. How physics is rewriting reality for centuries, time has been considered a fundamental pillar of existence, a relentless, unidirectional flow from past to future. But a growing body of research in physics suggests something radical. Time might not be a basic feature of the universe at all. Instead, it could be an emergent property, arising from the way information is encoded and processed within the fabric of reality. This shift in perspective, driven by advances in information theory and black hole physics, is quietly reshaping our understanding of gravity, cosmology, and even the nature of dark matter. The problem with time in modern physics, the traditional view of time, clashes with core principles of modern physics. Albert Einstein's theory of general relativity reveals time as relative stretching and shrinking based on gravity and motion. Quantum mechanics, meanwhile, treats time as a fixed backdrop against which events unfold, without explaining its origin. When physicists attempt to reconcile these frameworks, particularly at the quantum level of gravity, time often vanishes from the fundamental equations. The universe appears frozen, described by laws that don't account for change. This conundrum, known as the problem of time, has stymied physicists for decades. Entropy and the arrow of time. A flawed solution for years, the most influential explanation for time's direction has been entropy, the tendency of disorder to increase. Just as a shattered glass doesn't spontaneously reassemble, the universe appears to move toward greater chaos. This asymmetry explains why we remember the past but not the future. However, entropy doesn't fully resolve the problem. The fundamental laws of quantum mechanics don't inherently distinguish between past and future. The arrow of time emerges only when considering large-scale statistical behavior. More critically, it doesn't explain why the universe started in such an improbably low entropy state in the first place. The rise of information as a physical quantity over the past few decades, a revolution has been brewing in physics. Information is no longer just a mathematical tool. It is now recognized as a fundamental physical quantity, like matter or radiation. This shift was catalyzed by paradoxes in black hole physics. Stephen Hawking's discovery that black holes emit thermal radiation raised the terrifying possibility that information could be lost forever, violating a core tenet of quantum mechanics. Resolving this conflict forced physicists to confront a deeper truth. Information cannot be destroyed. Erasing it requires energy, and storing it demands physical resources. This realization has far-reaching consequences. Einstein's equations themselves can be derived from thermodynamic principles linking space-time geometry to entropy and information. Gravity, it turns out, may not be a fundamental force, but an emergent phenomenon, a result of underlying statistical processes, like temperature arising from molecular motion. Space-time as a memory medium, the most radical implication of this shift is that space-time itself might be a storage medium for information. Instead of being a smooth, neutral arena, space-time could be composed of discrete elements, each capable of recording quantum interactions. Think of it like a crystal lattice storing defects or a hard drive retaining data. Every collision, every interaction leaves an informational trace embedded in the fabric of the universe. This isn't just a metaphor. The present state of space-time reflects everything that has happened before. Regions with more interactions carry a different informational imprint than those with fewer. The universe doesn't just evolve according to timeless laws, it remembers. Time emerging from information imprinting recent research extends this idea to time itself. Rather than treating time as a fundamental parameter, physicists are showing that temporal order emerges from the irreversible imprinting of information. Every interaction writes something permanent into the universe's structure. Because this information cannot be erased, it defines a natural ordering of events. Earlier states have fewer records, later states have more. This perspective explains why time has a direction without invoking special initial conditions or statistical arguments. As long as interactions occur, time advances. The past differs from the future simply because the universe contains more information about the past than the future. Dark matter and dark energy, an informational explanation. Remarkably, this informational framework may explain some of the biggest mysteries in cosmology. Dark matter, the invisible substance thought to make up most of the universe's mass might not exist. Instead, the unexpected rotation speeds of galaxies could be explained by spacetime carrying an informational memory of past interactions. Regions with more imprinted information behave as if they have stronger gravity, boosting galactic rotation without invoking new particles. Similarly, dark energy, the mysterious force driving the universe's accelerated expansion, could also be a consequence of information accumulation. The irreversible spread of information may subtly alter spacetime geometry, mimicking the effects of dark energy. Testing the theory. A path forward, while radical, this informational approach makes concrete predictions. Black holes, where information is seemingly lost, provide a natural testing ground. The framework suggests that information isn't destroyed, but imprinted into spacetime before crossing the event horizon. The future of physics may lie in recognizing that time isn't a given, but a consequence of how the universe remembers. If spacetime truly records information, then the arrow of time isn't just a law of physics. It's an inevitable outcome of existence itself.